Around the same time that Thomson was studying cathode ray tubes, the discovery of radioactivity by Henri Becquerel provided a new tool for probing inside the atom. Becquerel placed a photographic plate that was completely sealed into a drawer with a piece of uranium ore. After several days, he developed the plates and found that spots had formed on them. Radioactive elements, like uranium, emit streams of particles and energy because their nuclei are unstable. Becquerel's photographic plates were exposed by radioactive emissions from the uranium.
Ernest Rutherford, who studied with Thomson, conducted many experiments with radioactive elements.
Rutherford's most famous experiment involved alpha particles, a type of radioactive emission. Alpha particles are positively charged, fast-moving, and have a mass close to 4 times the mass of a proton and 8,000 times the mass of an electron.
Rutherford realized that he could probe inside the atom using these particles. He devised an experiment to see what would happen when these dense, positively charged, high-speed particles collided with atoms in a thin sheet of gold foil. A narrow beam of alpha particles from radioactive polonium passed through a hole in a lead box to strike the foil. A circular fluorescent screen detected where the alpha particles hit after passing through the gold atoms.
Based on Thomson's model of the atom, predict the path of the alpha particles through an atom in the gold foil. Alpha particles are so small, so massive, and move at such high speed that Rutherford predicted they would pass right through the gold atoms with very little deflection. The path might be deflected slightly by the negatively charged electrons in the atom.
As expected, most of the alpha particles passed through the gold foil unaffected, and a few particles were diverted slightly. But a few of the particles seemed to strike the foil and bounce back. Rutherford said it was as if you fired a 15-inch shell at a piece of tissue paper and it came right back and hit you.
Rutherford realized Thomson's model of the atom could not explain these results. What caused the alpha particles to bounce back? Rutherford proposed that all the positively charged mass was concentrated in a small nucleus located in the center of the atom. Only a small, dense nucleus could reflect the heavy alpha particles. The electrons orbit around the nucleus.
But remember, most of the particles passed through the gold foil. What can account for this? Most of the particles pass through because the atom is mostly empty space. Rutherford's experiment suggested that the nucleus is very tiny relative to the size of the whole atom, and the electrons are very far away.
To give you a sense of how much empty space is in the atom, imagine this as a nucleus. Notice the electron labeled on your screen. Zoom out until you think the electron is the correct distance from the nucleus. If the nucleus was a P, the electron might be in the 38th row of the second-level balcony.
There is a lot of empty space in the atom!
Every seemingly solid object in our world is actually mostly empty space between particles held together by electrical forces.
Rutherford added up the mass of the electrons and protons and discovered that together they had less mass than the complete atom. In 1920, Rutherford predicted that the nucleus also contains another type of particle that has no electrical charge. 12 years later, the neutron was discovered by James Chadwick, confirming Rutherford's prediction.
In 1911, Rutherford proposed a new model. He described the atom as a miniature copy of our solar system. Electrons orbit the nucleus in the same way planets orbit our sun. But while the planets are bound in their orbits by gravity, electrons are bound in their orbits around the nucleus by electrical forces.
This planet-like motion of electrons introduced a new problem. According to principles of electromagnetism, any charged object that is accelerating should give off energy as radiation. As an electron orbits the nucleus, it is continually changing direction, and therefore constantly accelerating. So, an orbiting electron should lose energy. If an electron emits energy, the orbit should decay, causing the electron to spiral into the nucleus. But this doesn't seem to happen. The matter around us does not continually emit energy and collapse.
It was clear that Rutherford's model didn't explain all the mysteries of the atom. The next clue would come not from probing the atom as Rutherford did, but from within the atom itself in the form of light.